So picture this. You hand an AI a really complex task. It tries its best, completely fails, and then you ask it again, and it just repeats the exact same mistake. Right now, when our current AI models fail, teaching them not to do that again is a massive headache. It usually requires this incredibly expensive, computationally heavy retraining process, where we're updating millions or even billions of parameters just to fix one tiny blind spot. But what if we could teach an AI to learn from its mistakes simply by letting it talk to itself?
Welcome to today's Explainer. We're unpacking a really groundbreaking research paper that tackles this exact problem, and it does so using a radically simpler, honestly very human-like approach. The framework is called Reflexion, and the big idea here is reinforcing language agents not by tweaking all their internal math, but through plain old linguistic feedback.
Here is our roadmap for the explainer. We're going to start with the core AI learning problem. Unpack the actual mechanics of the reflection framework and break down how verbal reinforcement actually works. Then, we'll hit some real-world AI examples, break down the crazy results, and look at what this all means for the future of agents. Let's get into it. Okay, so to really get why this is a game changer, we have to contrast the old way with the new way. Traditional reinforcement learning, it requires a ton of compute. It essentially learns by mathematically updating internal neural weights. The result is a totally opaque black box process, where you have no real clue why the AI changed its behavior. But verbal reinforcement learning, specifically the reflection framework, is entirely different. It's super lightweight, requires absolutely zero fine-tuning of the model's underlying weights, uses plain, natural language to self-correct, and is highly interpretable. You can literally read exactly what the AI is thinking. To wrap your head around this, just think about human episodic memory. Say you accidentally burn your hand on a hot stove. Your brain doesn't just silently update some hidden matrix of weights. No, you mentally or verbally reflect. You say, ouch, yeah, I shouldn't touch that when it's glowing red. And you store that specific experience for the next time you cook, right? Hopefully saving yourself a trip to the ER. Reflection gives AI this exact same ability. It lets the agent iteratively learn from just a few tries by actively reflecting on its past failures. Let's break down step by step how this actually works. How does it turn a failure into a win? It relies on 4 main steps. Step 1, the actor, which is just a large language model, generates an action or some text. Step 2, an evaluator scores that action. Maybe it's just a simple pass or fail. Step 3, and this is the absolute magic part, a self-reflection model looks at that score and generates a verbal critique of what went wrong. And finally, step 4, that critique gets stored in the agent's memory to be used as context for the very next trial. When you map out the architecture, the whole feedback loop becomes really clear. The agent is interacting with its environment, right? And it's keeping track of its short-term trajectory memory, basically what it just did. But the crucial piece is its long-term experience memory. The self-reflection model takes the feedback it got from the environment, turns it into a reflective text summary, and drops it right into that long-term memory. So, when the actor steps up to try again, it is fully armed with a distilled, text-based lesson from its own past mistakes. The researchers sum up the crucial point perfectly here. Reflection converts simple binary feedback, like a 0 or 1, pass or fail, into rich verbal feedback in the form of a textual summary. This self-reflective feedback acts as what they call a semantic gradient. So instead of just getting a harsh wrong buzzer, the agent is getting a nuanced set of directions pointing it toward exactly how it needs to improve next time. Let's jump into our first concrete real-world example to see this in action. AlfWorld. AlfWorld is an interactive, text-based household environment. In one scenario, the agent gets a simple task. Examine the mug with the desk lamp. Now, the baseline agent completely fails. It wanders around, grabs a mug, but then just cannot find the lamp, wasting a ton of steps. But with reflection, the agent looks at its failure and literally writes a note to itself saying, I should have looked for the desk lamp first, then the mug. On the next trial, reading its own note, the agent completely alters its plan, searches the desk, finds the lamp, grabs the mug, and boom, success. It literally corrected its own flawed logic. When you track the success rate of this over multiple trials, the gap is just wild. Without reflection, a baseline agent quickly plateaus and just keeps failing on dozens of tasks. But the agent using reflection, through just 10 to 12 trials of trial, error, and verbal self-correction, it learns to solve 130 out of 134 tasks. That is an absolute 22% improvement over the baseline, just from letting it think out loud. Moving on to a totally different challenge, reasoning. Enter the Hot Pot QA dataset.
Hotpot QA forces an agent to parse Wikipedia articles and logically reason across multiple documents. Here's a task. Who has been in more bands, Johnny Craig or Pete Doherty? The baseline agent fails because it only counts the bands the musicians are currently in. But the reflection agent, when told its answer is wrong, stops and reflects. It writes, I did not take into account that Johnny Craig has been a member of more bands in the past. It realizes its own logical flaw. And without ever being given the actual right answer by the researchers, it updates its search strategy and gets it right on the very next try. The power of that self-correction is undeniable. Baseline agents get stuck in a rut, completely unable to probabilistically improve on the tasks they fail. But the reflection implementations climb steadily. Simply allowing the model to talk to itself about its reasoning mistakes yields a 20% absolute boost in performance. Okay, let's step it up to the ultimate test of this framework, code generation. Can we teach an agent to write, compile, and debug complex code in languages like Python and Rust? Well, in these tasks, the agent essentially acts like a senior developer, just, without the massive caffeine dependency. Instead of randomly guessing, Reflection lets the agent write its own unit tests. It runs the code it wrote against those tests. If the tests fail, it reads the compiler error logs, verbally reflects on where the syntax or logic broke down, and writes itself hints to fix the bugs for the next iteration. The results here are, honestly, they're staggering. 91%. That is the pass-it-one accuracy on the human-eval Python benchmark using this framework. Think about that for a second. The agent wrote perfectly functioning Python code on its very first final submission 91% of the time. When you compare the benchmarks, Reflection absolutely shatters previous records. On that human-eval Python challenge, the base GPT-4 model hit an 80.1% accuracy. The previous state-of-the-art was only 65.8%. Reflection pushes that all the way to 91%. And even on something like complex Rust programming, which is notoriously ruthless with compiler errors, Reflection pushes the base GPT-4 performance up from 70.9% to 75.4%. Now, to truly evaluate this research, we have to look at both its strengths and its limitations. Let's be real, it's not a flawless magic bullet. Let's take a dataset like web shop, for instance. Here, Reflection actually fails to improve over the baseline. Why? Because the agent gets trapped in a local minimum. Web shop requires extreme, diverse exploration across a complex e-commerce site to find a specific product. Verbal reflection alone can't really navigate that if the agent completely lacks the initial intuition of where to even look next. It just gets stuck. And there's another major limitation. The agent is entirely reliant on the quality of its own self-evaluation. Think back to the coding examples. If the agent writes a bad or flaky internal unit test, it might actually pass incorrect code. It falsely convinces itself that a buggy script is totally fine because its own test was flawed. But looking at the strengths, the fact that this requires absolutely zero expensive fine-tuning and gives us highly interpretable, nuanced feedback, that makes it a massive leap forward. So what does this massive leap in capability actually mean for the future of autonomous agents? The broader impacts here are profound. First off, because the AI's learning is happening in plain English text, we can finally open up the black box. Instead of trying to decipher billions of updated mathematical weights, human engineers can just read a transparent text log that tells us exactly why an AI made a specific decision. This pushes autonomous agents toward way greater efficiency, though obviously it requires robust safety monitoring. Because if an agent can teach itself to bypass errors, we absolutely need to make sure it isn't bypassing safety guardrails along the way. Let's quickly summarize our key takeaways for this explainer. The problem? Current AI repeats its mistakes unless we do expensive retraining. The solution? Reflection gives AI an episodic memory buffer so it can verbally critique its own failures. The results? Up to 91% accuracy, completely crushing previous coding benchmarks without a single weight update. And the impact is the dawn of highly transparent, self-improving autonomous agents. I want to leave you with this thought. We have officially moved from AI that needs to be spoon-fed millions of examples to AI that can simply talk to itself to get better. If a machine can now write its own code, test it, realize its own logical flaws, and verbally reflect to fix its own bugs, what is it going to teach itself to build tomorrow? Thank you so much for joining me on this explainer. Keep learning, keep reflecting, and I will see you next time.